Namaste children. Next, the magnetic effects of electricity. What do you mean by magnetic field and field lines? The region around a magnet where the force of attraction or repulsion can be detected is called magnetic field. Magnetic field around a magnet can be detected by using a magnetic compass. Magnetic field lines. Magnetic field lines are the paths around a magnet along which the north pole of a magnetic compass needle tends to move. The magnetic field lines around a magnet can be observed by sprinkling iron filings around a magnet. It can also be observed by moving a magnetic compass around a magnet. The magnetic field lines emerge at the north pole and merge at the south pole. The magnetic field lines are closer at the poles. The magnetic field lines do not intersect with each other. Magnetic field due to a current carrying conductor. If a magnetic compass is placed near a conductor carrying current, the needle is deflected. This shows that a conductor carrying current has a magnetic field around it. If the direction of the current is from north to south, the deflection of the magnetic needle is towards the east. If the direction of the current is from south to north, the deflection of the needle is towards the west. The magnetic field around a current carrying straight conductor is in concentric circle. It can be observed by passing a current carrying straight conductor through a cardboard and sprinkling iron fillings on it. So if the current is flowing from north to south, the deflection of the magnetic needle towards the east. If the current direction is from south to north, the deflection of the magnetic needle is towards the west. This is the diagram for a straight current carrying conductor which is passed through a cardboard on which iron fillings are sprinkled. When current is passed, they will align themselves in concentric circles. The path can be detected by placing a compass needle at one edge of the cardboard. Right hand thumb rule. The direction of the magnetic field around a conductor is given by the right hand thumb rule. It states that if a current carrying conductor is held in the right hand such that the thumb points in the direction of the current, then the fingers wrapped around the conductor shows the direction of the magnetic field. Here, all the four arrows will be the thumb points. Assume that and wrap your fingers accordingly and draw the field lines around these current carrying conductors. Magnetic field due to a current through a circular loop is passed through a circular conductor loop. The magnetic field produced is in the form of concentric circle around the conductor towards the center. The arcs of the circle become larger and appears as straight line. When applying thumb rule, if you observe all the circles, circular loop inside will be following the same direction and they are becoming larger and larger. At the center, they will become as a straight line. Magnetic field due to current in a solenoid. A solenoid is a circular coil of wire in the shape of a cylinder. When current flows through a solenoid, it behaves like a bar magnet. The ends of the solenoid behaves like the north and south poles of a magnet. The magnetic field produced by a solenoid is similar to the magnetic field produced by a bar magnet. The strength of the magnetic field depends upon the strength of the current and the number of turns of the coil. So B is the strength of the magnetic field. Mu is the constant. N is number of turns of the coil. L is the length of the coil. The magnetic field is concentrated into a nearly uniform field in the center of a long solenoid. The field outside is weak and divergent. The diagram of magnetic field around a solenoid. Always lines will emerge from the north pole and enters into the coil into the south pole, through the south pole, and the direction of the field will be detected by right hand thumb rule. Now, what is an electromagnet? A strong magnetic field inside a solenoid can be used to magnetize a piece of magnetic material like a soft iron when placed inside the coil. Such a magnet is called an electromagnet. If electric current is passed through a wire wound around a piece of soft iron, it behaves like a magnet. Such a magnet is called electromagnet. Force on a conductor carrying current in a magnetic field. A.M.Ampere suggested that if a current carrying conductor produces a magnetic field and exerts a force on a magnet, then a magnet should also exert a force on a current carrying conductor. For example, if an aluminium rod is suspended horizontally by a wire between the poles of a horseshoe magnet and current is passed through the wire, then the aluminium rod is displaced. If the direction of the current is reversed, the direction of the displacement is also reversed. The force exerted is maximum if the conductor is perpendicular to the magnetic field. This picture shows that a current carrying rod AB experiences a force perpendicular to its length and the magnetic field by the horseshoe magnet. So, if a force is applied on it, it moves out. So this is called as electromagnetic induction. The principle of electromagnetic induction is used in AC as well as DC currents. Fleming's left hand rule. The direction of force of a current carrying conductor in a magnetic field is given by Fleming's left hand rule. States that if we hold the thumb, forefinger and middle finger of the left hand perpendicular to each other such that the forefinger points in the direction of magnetic field, the middle finger points in the direction of current, then the thumb shows the direction of force or motion of the conductor. Electromagnetic induction, that is, a current carrying wire is placed in between two strong magnets, then the direction of magnetic which are held perpendicular to each other, then the thumb shows the direction of the force, that is motion of the conductor, and the forefinger shows the magnetic field direction, and the central finger shows the direction of the current. So this is Fleming's left hand rule, which is used in DC motors. What is electromagnetic induction? This was stated by Michael Faraday. The motion of a magnet with respect to the coil or a change in the magnetic field induces a potential difference in the coil and produces induced current. This is called as electromagnetic induction. Motion of the magnet with respect to the coil produces induced current. If a magnet is moved towards or away from the coil of the wire connected to a galvanometer, the galvanometer needle shows a deflection. This shows that current is induced in the coil due to the motion of the magnet inside the coil. The coil induced field is inside the coil. So, galvanometer, the current direction will be, the galvanometer will show the deflection out. If the magnet is pushed out, the current direction will be shown in opposite direction to the movement of the magnet. So this is induced field inside the coil. This is induced field out. When you are putting out, whether you are moving the magnet inside or whether you are moving the magnet outside, then the field is induced inside the coil, due to which the galvanometer shows the deflection opposite to the direction of the motion. When north is pushed inside towards the motion, the current direction will be shown. The galvanometer will be moving towards the current direction. When north pole is moving out, it shows the current direction also in opposite direction to the movement of the magnet. Change in magnetic field produces induced current. Take two coils of wires wound around a cylindrical paper roll. Connect one coil to a battery and the other coil to a galvanometer. If the current is passed through the first coil, the galvanometer needle shows a deflection in the second coil. If the current is disconnected, the needle moves in the opposite direction. This shows that current is induced due to change in the magnetic field, which is showing first coil is connected to a battery, whereas second coil is connected to a galvanometer. When current is passed by closing the key, there will be a deflection in the magnetic needle. This is known as induced current. So primary coil and secondary coil, connecting primary coil to a source, then current is passed, then current is induced in the secondary coil. This will be known by the movement of the voltmeter. This is due to change in the magnetic field strength in the secondary coil, which is by the primary coil, which is caused by the primary coil. This is known as induced magnetic field. Coming to Fleming's right-hand rule. The direction of induced current is given by Fleming's right-hand rule. It states that if the thumb, forefinger and middle finger of the right hand is held perpendicular to each other such that the thumb points in the direction of the motion of the conductor, the forefinger points in the direction of the magnetic field, then the middle finger shows the direction of induced current. So this is the thumb, motion of the conductor, forefinger, magnetic field direction, and central finger shows the direction of induced current. Direct and alternating current. Direct current or DC, a current that always flows in one direction only, is called direct current. The current we get from a battery is a direct current. Alternating current, a current that reverses its direction periodically, is called alternating current. Most power stations in our country produces alternating current. AC changes direction every 100th of a second and its frequency is 50 Hz. One advantage of AC over DC is that it can be transmitted over long distances without much loss of energy. When you plot graphs, the graph will be parallel to the x-axis in case of direct current, whereas alternating current, it will be like a transverse wave. Current reverses within 0.01 seconds. Coming to domestic electric circuit. Electric power to homes is supplied through the mains. It has two wires. One is live wire, positive wire with red insulation, and the other is a neutral wire, negative wire with black insulation. The potential difference between the two wires is 220 volts. The earth wire with green insulation is connected to a metal plate kept in the ground. Two separate circuits are used. One is of 15 amps for appliances with high power rating like geysers, air conditioners, etc. The other is of 5 amps for fans, bulbs, etc. The different appliances are connected in parallel so that every appliance gets equal voltage, and even if one is switched off, the others are not. The appliances having metallic body like electric iron, refrigerators, etc., their metallic body is connected to the earth wire so that if there is leakage of current, it passes through the earth and prevents electric shocks. So that if there is leakage of the current, it passes to the earth and prevents electric shock. Now, electric fuse. Electric fuse is a safety device used in electric circuit to protect the circuit and appliances from damage due to overloading and short circuit. Electric fuse. Electric fuse is a safety device used in electric circuits to protect the circuit and appliances from damage due to overloading and short circuit. It is a wire having high resistance and low melting point. If excess current flows through the circuit, the fuse wire melts and breaks the circuit. Fuse wire is made up of a metal or an alloy. Metals like lead, tin, aluminium and copper. Fuse wire is connected in series with the live wire. What is meant by overloading and short circuit? Overloading is caused due to increase in voltage or if too many appliances are connected to a single socket. It results in overheating of the wires and can cause damage to the circuit and appliances, which is known as overloading. Short circuit. Short circuit is caused when the live wire and neutral wire comes in contact and the current suddenly increases in the circuit. It causes spark, fire and damage to the circuit and appliances.